acid-base titration. Okay, this is more important. So here what we're doing is we're taking solution stoichiometry, which we just learned about in chapter 13, and the acid-base neutralization reaction, which we've learned about a couple of times now, and putting those together. So a titration, we have a substance in a solution where we know what the concentration is. We're going to react it with another substance where we don't know the concentration. The idea is to find out what's the concentration of that unknown thing. So if we're looking at HCl and sodium hydroxide, as with many acid-base reactions, here's our net ionic equation. So we're just going to look at the net ionic reaction. So here we have an Erlenmeyer flask with an HCl solution. We've left the chloride ions out of it just to make it simpler to look at. So it's got hydrogen ions. And then we have a burette with sodium hydroxide in it, and we've just shown the hydroxide ions, because the sodiums and the chlorides are just spectators. So as we add hydroxide ions to this flask, that net ionic reaction begins to occur. H plus OH minus makes water. So we add a hydroxide ion, it's going to react with one of these and form water. We add another one, it's going to react with another one and form water. We're going to keep adding this until we've reacted all of the hydrogen ions. The way we know that we're done is that we use an indicator. Phenolphthalein is the most common one. That's the one we used in our experiment. When you get just a tiny bit of extra base, then the solution turns pink, and that alerts you that you're done. So we're adding hydroxide to completely react with all the hydrogen ions in the solution. The equivalence point is where you have a stoichiometric amount of reactants, so everything's matching up just perfectly. We actually can't get exactly the equivalence point. We get what's called the end point, which is when the color change occurs. But if you do it carefully, they're going to be very, very close. So we carefully measure the volume of each solution. And knowing the concentration of the one solution, we can figure out what the concentration of the other solution is. So these are the calculations you're going to need to be able to finish that experiment. I believe it was 13B was the number of it. This is what it looks like. Here we've got a clear HCl solution, clear sodium hydroxide solution. As we add sodium hydroxide, we can see a little bit of pink forming here, but then when we swirl it so that all the hydrogen ions and hydroxide ions can interact with each other, the color goes away. And that will happen until one drop will cause it to turn pink. So let's look at how we would do a calculation here. A titration of a 20 milliliter sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What is the concentration in moles per liter of the unknown H2SO4 solution? So this is solution stoichiometry. Do not use M1V1 equals M2V2. Do not use that. We need a balanced chemical equation. We have a chemical reaction occurring. We're talking about 20 milliliters of H2SO4, and we're talking about 22.87 milliliters of KOH. Different substances. This is not dilution. This is a reaction. So first we need the balanced chemical equation. We've got H2SO4 reacting with KOH. Acid-base reaction, they're swapping partners. We've got H and SO4 2 minus, and we've got K plus and OH minus. And so over here, we've got K plus and SO4 2 minus, and H plus with OH minus, just swapping partners. So we're going to get K2SO4, and we're going to get H2O. We have to balance the equation. The reason we have to write out this equation is we need the mole ratio. So I have one sulfate and one sulfate, one potassium, two potassiums. So I need a 2 here so that I have the right number of potassium ions on each side. And then I see that I've got 2 hydroxide ions and 2 hydrogen ions, so that's going to make 2 water molecules. There's multiple ways to approach balancing that. The important thing is that you get to the right place. I'm going to take these away because they're messing things up. Now that I have the balanced chemical equation, I can use it to organize my information. 20 milliliters of H2SO4. I had 20 milliliters of this. And then I've got 22.87 milliliters of the KOH. And I've got a concentration of that, 0.158 moles per liter. And what I want to find, question mark, moles per liter. So this is just like the second solution stoichiometry example that we did in chapter 13. It's stoichiometry. So you first think about grams to moles to moles to grams. That's the starting point, and then you figure out, do I need to switch out one or more of the ends? What do I need to do? Well, here we're not given mass to start with, we're giving volume. And we're not finding mass at the end. So I'm going to take that moles, and I'm going to take the moles and divide by volume to get molarity at the end. Do you want me to tell you about millimoles? No. Well, millimoles can be pretty useful. I'll tell you what they are, and then I'll do the problem the other way. So here I have this molarity, right? 0.158 moles per liter. And I have a volume in milliliters. And that's annoying, right? Because these don't cancel out. So we had to convert the milliliters to liters, and that works. But you can also use millimoles. So if I put a capital M on the top and the bottom of that, does it change it? No, because if you multiply the top and the bottom of a fraction by the same thing, it's still the same answer, right? When I do that, millimoles and milliliters, then the milliliters cancel out. Milli means 10 to the minus third. It can be used in front of anything. You could have milli-inches. It's a little weird, but you could, right? Milli just means 10 to the minus third of that unit. So then when you use millimoles, and the next thing will be millimoles, and then you'll end up with millimoles, and you'll divide by milliliters, and you cancel out the M's, and you get molarity. So if that made sense to you, awesome, use it. If not, forget that I said any of that, and let's just do it the other way. So here I have a volume in milliliters, and so I'm going to convert that to liters. Before I start, it's 10 to the minus third, and 1 down there. Sorry, 0.02287 milliliters. Sorry, good grief, liters. Apply some common sense. Here, this is a small unit with a bigger number, smaller number, bigger unit. 22 milliliters is not 22,000 liters. It's not 11,000 soda bottles. So now I have a volume in liters, 0.02287 liters of KOH times, I want moles of KOH and liters in the denominator. Then I want to go to moles of H2SO4, and I need moles of KOH in the denominator. This will give me moles of H2SO4, and I can take that and divide by the volume to get the molarity. The molarity of the KOH solution is the conversion factor from liters to moles for KOH. So it's 0.158 moles per 1 liter. And then this is the mole ratio from the balanced chemical equation. 1 mole of sulfuric acid to 2 moles of KOH. .02287 times 0.158 divided by 2. 0.0018 3 sig figs. And that is moles of H2SO4. You could. You can do you could do the conversion for liters at the end. You could also string them all together and see that the conversions cancel out. There's so many variations here. If you're interested in seeing a different way, a more streamlined way of doing a calculation like this, I'd be happy to talk to you privately, but I don't want to confuse the whole class any more than I've already confused the entire class. So molarity is what we're asking for, right? What's the concentration in moles per liter of that solution? So here's my moles, 0.0018067 moles of sulfuric acid, and I need to divide by the volume of sulfuric acid in liters. So that's going to be 0.0200 liters. So I take that number, still my calculator, divide by 0.02. I get 0.090336. And I'm going to round that and get 0.0903 moles per liter, or capital M. Any questions? So in lab, what we did is we pipetted 10 milliliters of the soda into a flask, and then we added sodium hydroxide and measured the volume of sodium hydroxide needed to react to cause the solution to turn pink. And I wrote the concentration for the sodium hydroxide on the board. So that was given. You measured this, and you measured that, and so you'll do a calculation just like this to find the molarity of citric acid in the soda.